Okay, great, good. So thank you everybody for being here. So this is, we have adapted the schedule a little bit. So we'll see part one on essentially basic traffic models today, and then part two tomorrow. I will describe a little bit the distinction, but it will just be one flow that goes through over 2 days. So this is fundamentals on basic traffic models and traffic waves. And the first thing that should be stressed is that in these communities, it is just a golden rule that every talk on traffic flow must have a fundamental diagram, and every talk on traffic waves must show the ring road experiment. So I don't see it, but I imagine that the people in these communities are nodding and confirming this. So for that purpose, I already did my job on the first slide, and you see both of these plots here, but you will see them again over the course of the presentation. So I start out with just some basic traffic flow theory, really the fundamentals, and then little overview on what people do to model traffic flow. Then essentially go into macroscopic descriptions, then cellular descriptions, and then microscopic descriptions. Those three together form the most commonly used forms of traffic flow modeling. There are other ways to also describe it, for example, via kinetic equations or KDV type models that I think I mentioned in the very end, but for the purpose of practical simulation, especially with regards to autonomous vehicles, some of these are, as far as I see it, mostly rooted only in the mathematical community and have not yet transcended into the more application-focused community. So these descriptions here are ones that have found real application in practical settings, and that therefore is the focus here on these models. However, I will focus on the mathematical background of these different models and descriptions. So to start out on traffic flow theory, one first has to start out, of course, with stressing why modeling. So why traffic flow models? So of course, that is not just true for traffic flow, it's true for anything, right? One has to ask, why do you want to do models? And when I say models, I mean principled models. So models that are built from first principles and then maybe calibrated to data, but are fundamentally starting out from principle descriptions. In the times of big data, obviously, one could, in principle, try to just observe traffic flow, classify what one sees and measures, and then build essentially purely empirical models. And that can be done. But what I'm focusing on here is the complement to this, namely really starting principled models. The art, of course, is combining these approaches in practice, but the focus of this talk is largely on the principled description of traffic flow. So what does that enable you when you have succeeded in building a good model? Well, one is, of course, once you have a model, you can, in the model, reduce the system complexity. For example, take real traffic flow that's very complicated, replace different drivers by other ones, types of drivers, swap in an autonomous vehicle, and then that you have a model for as well, and then study what happens. Right? You can add and remove specific effects and modify them and understand what role they play. Again, once your model is good, and one has to be clear what good means, of course, right? You can study the effect of model parameters that you have in the model. It can be analyzed theoretically to a certain extent, mathematically via analysis. You can use computers to simulate. It can yield predictions, quantitative predictions. And also an interesting aspect about model is you can reverse the process. So model means that if I know how everybody drives, this is what it produce collectively, right, as emergent phenomena on the whole road, but you can also reverse the process. We can use models to compare what the model predicts about what would be the consequences of everybody's driving behavior and compare this to what we observe on real roads, and then reversely learn something about our individual driving behavior, because the fact is we don't really know exactly how we drive as humans. Another point that relates this to autonomous vehicles. So if one has a program on autonomous vehicles, why would one worry about traffic flow modeling, especially traffic flow modeling that does not involve autonomous vehicles? Well, the main reason is that if you look at the transportation system on our roadways right now, we as a society right now are fundamentally changing the system, right? By introducing different levels of automation and connectivity. And also, of course, electrification and shared mobility, right? So those are the four disruptive trends that are happening concurrently right now. Will, of course, continue for the next 1 or 2 or 3 decades, but this is really something that is striking. For the last 80 years, the way people drive on highways has not really changed very much. We just somehow people pick it up, they go out in the car, they drive. The road has become bigger and straighter and so on, but the general idea of people just go out and drive has actually not changed. And it's really just now, the last 5 years, that things are really changing right now fundamentally, with the introduction of more and more assisted driving devices in the cars. Other countries are a little bit further ahead of the United States in terms of building instrumented highways and connectivities and these kind of things. So it's really changing right now, right? The last 5 to 10 years that the big change happens, and that has to be understood. So one has to, specifically to autonomous vehicles, one has to understand and predict and model the impact of them, and hopefully prevent the worst pitfalls in a principled way to understand what the impact will be and can be and could be, and hopefully then help and guide the design and deployment of these and the policy decisions that one doesn't get negative consequences, but actually can reap some of the positive benefits. Now, when you talk about models, the most important message that you always need to keep in mind about any model, but particularly about traffic flow modeling, is the quote commonly associated to George Box, is all models are wrong, but some are useful. So if you take one message out of this talk, that's it, okay? You will see that there will be gross simplifications being done in the models here compared to how real traffic flow looks like, but that does not mean it's a bad model. Yeah. So simplicity in itself is neither a merit or a pitfall. It can still be a useful model or not. Now, whether a model is useful or not depends, that's the second message, depends on your situation, what you're interested in, what you need to. It's not that a model intrinsically is useful or not useful. It depends on what you want to predict. So for example, if I want to know the precise trajectories of all the vehicles, and I use a description that doesn't track the individual vehicles, but only zooms out and takes a rough averaged evolution, I will not be able to, the model is incapable of giving you precise trajectories. On the other hand, if you don't care about precise trajectories, but just the large scale evolution, then such a model might actually be perfectly suitable and superior to one that actually tracks the detailed the trajectories of all the vehicles. Okay, so the answer is also it depends. All right, so these are sort of the fundamental things. The next thing I want to invite everybody, I actually put just on my website, you see the link there. If you copy it over to your browser, you can download this data set. This data set is not by me, okay? So this is the Seminal NGSIM data set. Now, quite aged, so it's been around definitely for a decade. And this data set that I put there is 3 15-minute slabs as data sets from Emeryville, California, with some camera systems and the data processing. It's the precise trajectories of all the vehicles on this segment. And essentially what I provide here is just these data. And I added, this was done together with Dan Work, essentially just a file, a MATLAB file called animate ngsim that you can just use to run the video, to plot essentially the evolution in real time. So sometimes you have people from the more theoretical side or from other fields that have not dealt with traffic flow data. This is your opportunity. Yeah, so just go to this, download it. Just to be clear, it might slow down your internet connection. Downloading is not a tiny data, so there's the files are each about 200 megabytes, so the whole thing is about 700 megabyte total. So watch out, but if you want and you have MATLAB available, you can just open it up and do load trajectories here as it is, and then just type animate ngsim or just run the file, and you should see something pulled up that shows you the trajectories, how they move around, and you can look at them and study them and use them. So for anybody who says it's so hard to get started on data, which is true, right? Here's your opportunity to get started. Okay, so copy and paste just the text on this page. Oh, you cannot copy and paste, sorry, this is probably screen share. Well, somehow type it or search my website and then just ngsim.zip and download this. All right, so let me move forward. Now, traffic flow. On on the top is an idealized view of traffic flow. All the cars are exactly equispaced, drive all with the same speed. At the bottom, of course, it's more like how it would look in reality. But let's start at the top, right? So vehicles have all the same length on a highway, which of course we know is not true, but it can still be a useful model to simplify it this way. Vehicles have velocity u, I call u here the velocity, and then you of course have to distinguish spacing from gap. So the spacing is front bumper to front bumper of successive vehicles. The gap is rear bumper to front bumper. Ultimately, the gap is really what governs your driving behavior, right? How you adjust to the vehicle. And of course, in principle, you could generalize this to different vehicle lengths as well, right? These descriptions. But for simplicity, let's take all the vehicles are identical length and identical drivers and everything. So with this setup, you can look at the vehicle density. Vehicle density essentially means you have the number of vehicles per unit length at a fixed time. And in particular, you get rho max, the maximum density on the road, which is essentially arising when vehicles are bumper to bumper plus some safety distance, right? So L plus 50%, right? So L times 1.5, and then the maximum density is 1 over L times 1.5. That, of course, you can observe empirically also on the road when you have a stoppage, right? How many cars per kilometer will you have? And it's generally around 133 cars per kilometer per lane that you get. So that's the density, of course. Obviously, that's not a vehicle. A single vehicle doesn't have a density, right? You need a collection of vehicles. So this is already not a microscopic quantity, meaning a single car-focused quantity, in contrast to the speed, right? Or the gap, which you can define when you just have two vehicles. For making sense of a density, you need more than one or two vehicles, right? You need to zoom out enough and look at a sufficiently long segment to actually make sense of this is a density, right? So therefore, density is actually not a microscopic vehicle-centric quantity, it's a macroscopic quantity. Flow rate, or sometimes called throughput, or in water flows, it would be discharge in other terms, right? All the same thing. That is the number of vehicles passing a fixed position per time unit, right? So you're standing next to the road and you count how many vehicles pass you. Well, you or some detector, right? Some sensor, camera, loop detector, and so on. So again, that's obviously a macroscopic quantity now in time, because you cannot instantaneously in time define that's the flow rate right now. In reality, right, you need to take a segment in time, like let's say 30-second interval, and then count the vehicles that go through. Okay, and then with the flow rate Q and the density rho, you can get the velocity. Well, if all the vehicles now are at the top going at the same speed, then of course every vehicle has a velocity u, right? Which of course is distance traveled per unit time. If you are at the bottom situation, then of course vehicles all have different velocities. So you have a vehicle-specific speed that every vehicle is going with, but you can also define a macroscopic velocity that corresponds to essentially what is in that segment of road now in space-time, right? A slab. What is sort of the effective average speed at which the flow goes? And that, what is called bulk velocity, is defined as exactly the flow rate divided by the density. You can, of course, check dimensionally that this gives you the right units. And I see a raised hand here.
Yes, the question would be, you have two-lane road. Does it make sense to calculate a flow rate basically for both lanes together, or would it make more sense to calculate them per lane?
Yeah, so both can be done, and the answer is, as usual, it depends. It depends on what you're interested in. So, for example, it could be that you have data from GPS where you don't actually get information about in which lane the vehicle is. Then a lane aggregated description is needed. There's no point in trying to separate it out. If you have camera or loop detectors that distinguish the lanes, you would have information about it. And then the second question is, what are you interested in, right? What's your answer? If I just want to know, where do I get the biggest amount of congestion and people can move freely between the lanes, probably lane aggregated description will suffice to capture this. If you, however, need to model something like, well, there's an off-ramp, an exit-only off-ramp coming up, for example, then a model that will just aggregate the lanes up to that off-ramp might actually be insufficiently accurate in describing the phenomenon. So the answer is definitely here, it depends, but both can be done. All right, so bulk velocity, right? So that is, I associate a speed to sort of a segment of highway in space-time, right? And that would be the bulk velocity. That is flow rate divided by density. which is just almost like the definition of flow rate and a definition of density. But also you can check that in terms of dimensional units, this makes sense. This is an important distinction. And of course, you can think of this as an analogy to fluid, right? Fluid flowing in a pipe on a river or something. If you throw leaves on a river, not all the leaves will move parallel to each other with the same speed, right? Different leaves will move at different speeds. In different parts of the river, more to the center, it flows faster. To the sides, it flows slower, right? But you can still define an average flow of the river, and that would be exactly the amount of flow that happens. You can define an average speed, right, as just dividing the flow rate of the river, how many water molecules get moved, divided by an analog of a density, which in this case would be essentially the cross-sectional area that is covered with water in this case, right? So it's the same idea in traffic flow as well. And then, of course, there's the microscopic relationships between these quantities. But that's important to distinguish really the microscopic perspective and the macroscopic perspective. And one thing also that one has to see is data, right? So in data, traditional data that's collected by agencies is usually you deploy sensors, loop detectors or cameras on fixed positions on the road, and they count vehicles. So these data that you get often after traditional data are intrinsically macroscopic because they count vehicles over an aggregated interval. So one has to keep this in mind when one has to decide, do I want a microscopic model, for example, or a macroscopic model? Whereas GPS sensor data usually track vehicle trajectories. So they track the microscopic, they report back the microscopic speed up to the error bounds that you can extract this from GPS. And that then might give rise to potentially different models that you may be inclined to use based on the data that is available. Okay, so model decision, what to use, it has to depend both on where do I get my data from, and also, of course, what am I interested in the end. All right, now, talking about traffic flow theory, Bruce Greenshields that you see in the top left doing his PhD thesis using this innovative device called a video camera. He is the father of traffic flow theory. In 1933 already, he produced the first empirical but systematically tabulated relationship of the speed of traffic flow as a function of the density of the vehicles. And you see here collected these data points, right? And he noticed that, well, unfortunately for him, you don't see too much congestion on that road because there were not that many vehicles on the road yet. But he found one spot somewhere else, and you can ask Dan Work for some stories about where somewhere else that was, because it's quite funny. So another data point, and you see that these data points lie beautifully, suspiciously beautifully on a straight line, but that was what he observed. And of course, if that's your relationship of speed as a function of density, just being an affine linear relationship, then of course the flow rate, which is the product of speed and density, right, will just be a downward facing parabola. So this red curve is what then is called the Greenshields flow rate, or the Greenshields fundamental diagram, because if you plot the flow rate versus the density, that is what is called the fundamental diagram of traffic flow. In part because it gives you the relationship between these two quantities, but also in part because that's what traditionally loop detector units or cameras that are pointing downwards and count vehicles, that's what they measure, right? So they measure the flow rate by just counting the vehicles, and they reconstruct the density either by, if they can measure velocity directly, by then inferring the density on this, or if not, use other tricks to get this. But this is close to what is also measured. And you see the Greenshields fundamental diagram that follows out of his measurements, and then you see some more contemporary measurements. And of course, you see that ultimately, this is not, the Greenshields fundamental diagram is not a very good description, in particular the fact that the maximum flow rate, so this critical density that you get, happens exactly at half the maximum density. That, of course, is a property of having a downward facing parabola, but that is 0 here and 0 here. But of course, you see that in real traffic data, the critical density happens at much lower densities than 1/2 of the maximum density. So that's the fundamental diagram that you see here. You could, of course, put in a different function that still is smooth and concave down, but goes more through the middle here, which is done here just by essentially doing a fit, right? A weighted least squares fit to put this in. So this is different things you could do if you wanted to put this in. the very intriguing thing about fundamental diagrams, I wrote this here, is that pretty much everywhere in the world where you collect data carefully and you have a segment of highway where you also have congestion, you will observe this characteristic shape. And that's true for different countries, even where rules of the road are different, like Germany, for example, where you under no circumstances can overtake on the right, versus the US, where it's common, where you have bigger speed differences along the roads. For example, Germany versus the US, you still get fundamental diagrams that characteristically show that for low densities, clearly what is called free flow here, right? You get a very small amount of spread that's mostly rooted in the fact that different peoples have different comfort zones on how much they are comfortable exceeding the speed limit. And then at some point, it starts become spread out, systematically spread out. You see the general trend is decreasing here, right? So resembled in this black curve here. But what's characteristic in this congested regime, so this maximum density, the density of maximum flow rate is called the critical density. Everything to the left is free flow. Everything to the right is congested traffic flow. But you see that in reality, you always get a spread here. That always arises. Another thing that is visible here is that you get this sort of funny drop here. That is somewhat debated how systematically real this is, but that's what people call capacity drop. And some people believe very strongly in that it's systematically always there. Other people say it might be artifacts, but this is something that people also give names to. And then also there's the traffic phase theory by Boris Kerner and collaborators, where, for example, you distinguish a free flow curve here then from something that's called synchronized flow. And then one can also squeeze in extra regimes that might be called wide moving jams or other ideas. So empirical descriptions of what is being observed, but then also, of course, mathematicians look a lot at models and see which types of models reproduce some of these empirical descriptions. All right. So, and this spread, by the way, this is still an open question from my judgment in traffic flow theory. A precise phenomenological understanding of which different aspects cause how much of that spread, right? So, of course, there's sensor noise always, but there's also inhomogeneities across drivers and vehicles. But there's also non-equilibrium effects like stop-and-go waves, for example, that also are known to contribute to this. How much contributes to what, right? And there is one of the key open questions, actually, in understanding this really in traffic flow theory. All right. So far, so much about fundamentals of traffic flow theory. There's a lot more one could do, but that's it for now. Now, here are three major examples of different descriptions of traffic flow. One is microscopic. Essentially, you describe the individual trajectories of every single vehicle. For simplicity, single lane, right? Single lane, cars follow each other, no ramps. And then you see the trajectories here, you see the positions of the vehicles here, you see time, and then you see some waves here, right? Car goes, accelerate, then suddenly brakes. Accelerate, brakes, right? So here you see traffic waves, for example, happening. And the model, for example, could be an adaptation of Newton's laws of motion. The acceleration of the jth vehicle is some nonlinear function of the distance to the vehicle ahead, its own speed, and the speed of the vehicle ahead, for example. So this could be an example of a microscopic description. In contrast to that stands the macroscopic description, where you adapt equations of fluid dynamics to deal with the quantities like rho, the density, or rho times u, which is the flow rate, q, that we talked about before, and actually don't aim to resolve the individual trajectories. Don't aim to predict where will each vehicle end up being, but I want to only predict the averaged quantities. So the aggregate bulk quantities. And then you might get something like a density as a function of space that has such a discontinuity, a jump here, right, a shock, and then you can get traveling waves, for example. I will show a little more on this. All right, I see another raised hand showing up.
Yeah, I'm looking at the microscopic model, and I was wondering if you could elaborate more on x, the variable x means in the difference equation.
X is a continuum variable. It essentially means the position on the road. So you have a one-lane road. You have, say, a segment. You have an inflow here. You have an outflow here. X equal to 0 is the inflow. And as X increases, that is a downstream going along the road. So that's the position of the vehicles along your 1D road. And this is time here. So these are really the trajectories plotted. Each trajectory is just the position along the road as a function of time.
And U is the the velocity?
You would be the speed. So that would be xj dot, right? So one could write xj double dot here, right? So dot is time derivative. So this is the acceleration of the vehicle. And then uj is nothing else than xj dot. Yes.
Okay, thank you.
Yeah. And tomorrow I will talk much more about microscopic models.
All right.
All right. So here, no need to understand this here, right? So this is a complicated 2x2 system of hyperbolic conservation laws. What is important is that it is described in terms of the macroscopic quantities that are not the vehicle-centered, but the average quantities, and it resembles equations of fluid or gas dynamics here, and makes use of some of the knowledge that is established, but is suitably adapted to capture things in traffic flow that are different from moving gas particles. And then there's cellular models. I will highlight either towards the end today or the beginning tomorrow, some differences in what could people mean when they mean cellular models. But one way, for example, are cellular automaton models, where essentially you chop up the road into cells that are not real. Of course, they're virtual cells, right? But you idealize it, and a cell can either be occupied by a car or not. And then you have certain rules how this propagates. For example, one example of this is the Nagel-Schreckenberg model that is actually being used in Germany for some highways to do simulations. And you also see these characteristic waves that go backwards. Here, time is here and x is here. I've just taken this picture from Wikipedia here, but you see that you get these characteristic waves, stopping-go waves, essentially, that travel backwards along the road. Right? So all of these actually show traffic waves that are important non-equilibrium effects that actually happen on real roads when traffic is sufficiently dense. So again, the idea of microscopic models is to describe the behavior of individual vehicles, right? And of course, if you have heterogeneity, systematic heterogeneity across vehicles, like you have a big truck immersed in a sea of passenger vehicles, or a single autonomous vehicle, then obviously a microscopic description is very natural to capture this because you're resolving every single vehicle. On the other hand, if you don't have data available about the individual vehicles or you don't care about it, these models would have unnecessary degrees of freedom, and a macroscopic description might actually be more suitable. Also, if you have incomplete, sparse data and you need to adapt it in a way, the macroscopic framework provides more natural ways to do that. Privacy, right? If you have a model framework that don't tracks individual vehicles, this can be much more suitable to considering aspects and constraints like this. So again, which model is best depends, right, again, on what you have available and what you're interested in using. Cellular automaton models are very easy to implement and very quick to run, very trivial to parallelize. So there's a decision to be made, but one thing that should be stressed is that mathematically these models are related. So specifically, if you take a microscopic description and do a proper scaling of the vehicle length and the vehicle interaction distance and the number of vehicles on the road, you can actually establish that they converge in suitable limits to a macroscopic description. And the same is true for the cellular models as well. If cell size going to 0, you can establish macroscopic models as limits. So these models also stand somewhat central, these macroscopic PDE models, as suitable limits of these individual descriptions as well. Okay, so these are the sort of a rough overview on very popular classes of traffic models. Now, in each of these models, or certainly in the microscopic and macroscopic models, one thing I want to stress is the distinction of first-order dynamics versus second-order dynamics. So in a nutshell, first-order dynamics means that given what the state on the road is, you prescribe what the speed is that the vehicles choose. Whereas second-order dynamics means that given what is the state right now on the road, you prescribe in your model what the acceleration is that the vehicles choose. Okay, so therefore, first-order dynamics is just one time derivative prescribing speed. Second-order dynamics means you're prescribing two derivatives, so you're prescribing the acceleration. And the general trend that is observed or structure is that first-order dynamics are able to produce, for example, shock waves, so moving an upstream end of a traffic jam, for example, green-red dynamics and so on. But they cannot describe dynamic instabilities in traveling waves like stop-and-go traffic waves or phantom traffic jams. These usually arise only when you have second-order dynamics, assuming your model is local in time. So your state depends on what is currently present right now. That, of course, again, is an idealization of reality. If I drive, I probably take into account what happened over the last 10 seconds which will be non-local in time. So if you have delay or integral differential equations, then of course also with first order dynamics you could reproduce some of these effects. But again, you have to keep in mind the goal is not to capture every single aspect of reality, right? The goal is to find a model that is simpler than reality so that it allows you to get useful predictions out of it. Yeah, so I'm focusing only in this presentation on models that are local in time, because it's a can of worms to introduce delays, to simply speaking. All right, so the macroscopic first order right would just be xj dot, for example, the speed that a car chooses some nonlinear function of the distance to the vehicle ahead. Yeah, and second order dynamics would be the acceleration of a vehicle is some nonlinear function of the distance to the vehicle ahead and the two respective speeds, for example. So there's lots more modeling freedom that one can choose. Likewise, a first order macroscopic model would just be a scalar hyperbolic conservation law that just describes the evolution of the density, versus second order model would be one where you have a density field and a velocity field as independent quantities, and then you have two equations. One describes the conservation of vehicles, one describes the actual driving behavior, so how you accelerate and brake, and then has adaptations of fluid dynamical equations here. All right, that was the overview on traffic models. So let's dive into macroscopic traffic models. So the philosophy, I said this before, so let me just quickly recap here. So the philosophy of macroscopic models is to use the equations that are macroscopic density, flow rate, and so on, and cast models in that framework. Usually they are lane aggregated because you can, and it simplifies your model, but you can also use that for a multi-lane description. It's a natural framework for multi-scale phenomena because you can zoom in and out once you have the macroscopic description as you wish, right? So traveling waves are easy to cast in this framework. Shocks, idealizations of braking zones, and they simplify your mathematical description, actually. There's an established theory of, for example, control and network coupling conditions. It's good to use with sparse data. There are established ways to do filtering together with sparse data. The mathematical relation to other descriptions, right? Suitable limits we mentioned. And of course, they're fun to analyze as well. There's established numerical methods for these type of descriptions. So this is really the use case. But again, to be clear, right? So if you're interested in features that have a higher level of granularity than these macroscopic quantities, these models have no chance of resolving them, right? So if you want something that really distinguishes on what happens with one vehicle exactly compared to next the other one, these purely macroscopic descriptions will probably not suffice. Yeah, so it always depends on what you want to do. Nevertheless, they play an important role. So at the core of any macroscopic model is the continuity equation. So essentially you take a highway, 1D, x is the position along the highway, t is time, you have a density, rho, and now you take an arbitrary segment from A to B, and you just integrate the density. And definition of an integral of a density of a space is that's the number of vehicles on that segment, right? So density evolves in time, so therefore the number of vehicles on that fixed segment changes in time. Let's call it m of t. You have your flow rate. I called it q before, now I'll call it f, just because f is what mathematicians use for flow rate. And we saw before it's rho times u, so density times speed is the flow rate. And now you just say, okay, what's the rate of change of the number of vehicles on this segment from A to B? Well, first of all, obviously, by using the definition of m, it's just the integral from A to B over OT, right? A and B are independent of time, so I can pull the differentiation in the inside. Subscript t means it's a partial derivative, because now I have a two bivariate function here, right? So I need to be careful that it's a partial derivative now, but that is just simple basic calculus. Now, the rate of change of the number of vehicles in that segment, well, there's no ramps, there's no cars being dropped onto the highway or removed, so the number of cars in that segment from A to B can only change in time by how many cars flow in on the upstream end, A, right, and how many cars flow out of that segment on the downstream side, B. So it's the flow rate of A that adds to the number of vehicles, right, minus the flow rate of B that takes cars away. So the rate of change of cars on that segment needs to be f of A minus f of B. And now this difference can be written using the fundamental theorem of calculus backwards, can be written as the integral from A to B over the x derivative of the flow rate, right? So this is just fundamental theorem of calculus. And now you see that this integral of a to b of rho t needs to be equal to this integral of minus fx. And that needs to now hold for any arbitrary choice of a and b. So the only chance for this to work is that the arguments under the integral sign agree. So you get rho t plus fx is equal to 0, or rho t plus rho u x is equal to 0. That is called the continuity equation. It essentially is just conservation of mass, conservation of vehicles. This is not specific to traffic flow. This is true for any flow where you're not losing particles. So that is an important fact. The other thing is it's a principle. This is not a model in itself, right? It's just a principle. So there's been no modeling, no assumption about how people drive, right? It's just a fundamental principle that holds. Also, of course, it's not a model. You see it because you have two unknowns. You have the density field and the velocity field, right? But you only have one equation, so that doesn't determine anything yet. It's just relating these two fields. So how can you make this into a model? Well, the simplest way to do it is you prescribe a relationship between the density and the velocity. So specifically, I say the velocity is some function of the density. That then induces the flux function q of rho, that's just rho times u of rho. And that then will make this a scalar hyperbolic conservation law that is a whole field of mathematics that is well understood, and one can really understand how these solutions behave. And in a few minutes, I'll talk a little bit about that. But that's not the only thing one can do. One can also, of course, say, well, I leave the rho field as it is, and u as an independent quantity, and now I add a second equation. And then again, I have two equations, two unknowns, and then I get a system. For example, a system of hyperbolic conservation laws, or something with second derivatives, but I can formulate systems of partial differential equations. And what is the right description? There's no ground truth. It depends on how well it describes in reality and what you want. For example, right, this first order description, that is generally called the Leiter-Witham-Richards model. That's a first order model in scalar hyperbolic conservation law. And then there are these second order models that are two equations here, two examples. The first one was the Payne-Witham model, independently proposed by Witham and Payne. This is an adaptation of gas dynamics here with some pressure and some relaxation term here. The important part is here that what was the speed u that cars instantaneously assume, here now becomes a desired speed that depends on the density, and the cars relax in time via acceleration and deceleration. So ut plus ux is the acceleration of a vehicle. That's a rate of change of speed in a moving frame of reference. That now is just a relaxation term. So you have a desired speed u now. That is coming from data, for example. And your speed, instantaneous speed, relaxes in time on a time scale tau towards that desired speed. And then there's some pressure that kicks in when cars get too close, essentially to prevent collisions and mathematically make the model well posed. All right. Now, time permitting, I will talk a little more about these models, to mention some differences here and so on. For now, the main point is there are second order models. And an important question is, of course, do you need them or do you not need them? And I'll try to highlight, of course, what does it mean, right? What are the fundamental differences in terms of what they can produce, second order models versus first order models? And then this could guide you, if you want to talk about traffic flow and how your autonomous vehicle interacts with traffic flow, what description is suitable for what you need. But let's start with the first order model and understand this a little more mathematically, what it actually does. So again, one starts out with a continuity equation, has the rho and the u, and then closes the model by prescribing a relationship u of rho. What's the simplest principle? Well, let's say if I'm alone on the road, right, if density is close to 0, then I drive with a u max. That's usually the speed limit plus a little bit. When the cars are bumper to bumper plus some little safety, so at rho max, that's usually when traffic comes to a complete stopping. So that's what people call the jam density. So the speed is 0 there, and then the simplest ad hoc function that would concern these 2 points is one that just goes linearly through, right? So linear interpolant in between, so I get that u is just some u max times 1 minus rho over rho max, so this linear function. If you take that, it induces the flux function here, so the flow rate, as this downward facing parabola here, just the speed function multiplied by rho. And of course, we know that one could do more realistic functions, but that is that's the Green-Shields flux function that just results from this linear relationship. Real speeds will be more constant here and then drop more rapidly, right? And then reproduce something like this. This can all be done. Okay, now, but let's stick with this simple description for the sake of argument. One thing is now, can I understand what this hyperbolic conservation law with this flux function will do to an initial profile, will do in time? To understand that in mathematics, one can use what is called the method of characteristics. So the method of characteristics is nothing else than saying, okay, I'm interested in the rate of change of the density, but here, this is the rate of change of the density at a fixed location x. Instead, I'm asking, what is the rate of change of the density along a curve, so a moving observer. Think you have a frontage road next to the highway, you have a motorcycle, you drive the motorcycle along a trajectory x of t, so with speed x dot, that's the speed of your motorcycle, but that speed is different from the speed of the traffic flow that you get, okay? And then you measure right next to you, what is your density right next to you, right? You have a camera that attracts this, and you want to know what is the rate of change now of the density along that moving frame of reference. Well, by chain rule, you get that this is equal to rho x, the x derivative, first argument here derivative times x dot in a derivative, plus rho t. Rho t, however, we know is minus fx by using the equation, so we get this here. And minus fx is f prime of rho times rho x. I'm assuming everything is differentiable here. And then we get the rho x here, we pull it out, and we get x dot minus f rho. And now I ask, how can I choose the speed of my motorcycle, x dot, such that this description becomes particularly simple? And it becomes particularly simple if I choose x dot, the speed of my motorcycle, equal to f prime of rho. If I choose that speed equal to f prime of rho, then this term will be 0, and I will get that the rate of change of the density is 0, meaning the density next to my motorcycle remains constant in time. That's as simple as it can get. So therefore, the method of characteristics say, let me drive my motorcycle with that speed, and then my density will be conserved along these special curves here. So along these curves, the density is conserved, and f prime of rho, look at this downward facing parabola, will be this function here. So it will be equal to U max for low densities, then it will be 0 for the critical density, and then it will be negative for in the congested regime of traffic flow. So there you have backwards going information. Cars always go forward on the highway, right? But information travels backwards if you're in the congested regime. Very important fact that, of course, is important for traffic jams, for example, moving backwards along the road. Okay, and then, of course, it induces this evolution here. So the light blue curve is the initial condition, and then in time, right, after some time, points that are congested move to the left, density values that are in the free flow move to the right at a speed that is 0 here, and the biggest down here, and the biggest backward speed up here. That, of course, again, is not the vehicles, it's the information that is traveling, right? So information is traveling backwards here, information is traveling forward. So if you start with this nice symmetric Gaussian, this will flatten where the spatial gradient of rho is negative, and it will sharpen the profile where you have increases in density. Okay, so that's what the method of characteristics tells you. So you see in time that after some further time, it looks like this, and after some further time, it looks like this. Okay, beautiful, except for that this is not a function. Yeah, you see here at this point here, of course, I have 3 values for the density. That, of course, does not give you a function. In reality, if the model should hold, yeah, it needs to predict one particular value at each position. So there's a mathematical and a practical problem here that must be remedied. One way, of course, to say the model breaks down, it ceases to be a suitable description of traffic flow. But of course, reality continues beyond this. So the question is, can we save the model and still make predictions beyond that time of wave breaking that you get here? That just follows from the properties. And the answer is yes, it can be done. This is, in mathematics, the concept of weak solutions. The main point is that one says that what happens beyond that time is that there's a shock. A shock is a traveling discontinuity that then we make sense of mathematically be part of the solution. Obviously, a shock, a traveling discontinuity cannot be a solution of the differential equation. Let me go one slide back, because this differential equation differentiates things, and discontinuous functions you cannot differentiate, at least not in the sense of functions. So one needs to make sense of this mathematically, which can be done. Physically, what it means is that you have a traveling discontinuity, a shock, that is an idealization of reality. In reality, of course, there will be a transition zone, a braking zone, where cars brake, slam their brakes. But the idea is that relative to the length scales that you're interested in, a mile, 10 miles, this braking zone will be very slim. and therefore you can idealize it by a traveling discontinuity. Yeah, again, all models are wrong, but some are useful. So this would be a mathematical idealization of reality, collapsing the breaking zone into one single discontinuity and then describing, reducing the dynamics of the breaking into essentially jump conditions that describe the dynamics of the shock. So that's the last sentence here. So that would, for example, be an upstream end of a traffic jam, right? Where you have a low density state and a high density state, and in between you have that traveling discontinuity, the upstream end, the braking zone, where you see the red lights and people turning on their flashers sometimes. Okay, so if you plot this in X and T diagram 10 going up here right now, you have all these curves, and then at some point they intersect, right? And here's the zone where you need to fill it in by a shock that moves along a certain trajectory here, and that needs to be defined. So what is the proper definition or notion of a shock speed that you need so that it still satisfies the fundamental principle of conservation of vehicles? So, well, first of all, the first time, if you start with a smooth initial condition, the first time of the wave breaking, of the breakdown, will happen as essentially this quantity here, can be just calculated when is the first time the curves intersect. So reality exists beyond that time, as we said, so one needs to make sense of this. And one way mathematically to do it is that you introduce weak solutions. In a nutshell, what happens, what you do is you take the differential equation, you multiply it by a test function phi that is compactly supported and smooth, that you can differentiate it. And then you take the solution, the differential equation, you integrate over space and time, and then you use partial integration to throw the derivatives onto the test function. Because the test function is differentiable, that can now, this formulation now can make sense also for rows that are discontinuous. And then you say, I call something a weak solution if, like rho of x and t, if it satisfies this relationship for all possible test functions. And of course, any solution, any weak solution that happens to be smooth is of course also a classical solution, a traditional solution, because you can just undo the integration by parts and confirm that it satisfies the PDE. But this concept now has more solutions because it also holds for some functions that actually are not differentiable, that are non-smooth. So the weak solution concept is wider than the concept of classical solutions. In particular, it allows for traveling discontinuities. The simplest setup is one where you just have the infinite road, infinite to both directions. You have one density rho L to the left, upstream, one density rho R on the right, downstream. Then you have a shock in between. And now the question is, what is the speed of the shock? Well, the speed of the shock needs to be so that you have conservation of vehicles. So let's check this. So such a problem is called a Riemann problem, and conservation of vehicles means, or let's check this, right? So if I look over time, right, time, initial time, final time, the shock has moved. So in that segment from A to B, I have fewer vehicles because the shock moved to the right and it was an upwards jump. So I have fewer vehicles, and how many vehicles have I lost? Exactly the area of this rectangle here, right? The area of rectangle is rho L minus rho R times S, right? This would be negative, so I lost vehicles here, and that must be equal to, of course, the influx minus the outflux by the conservation principles that we saw before. So therefore, you just divide this difference to the right, and you get that the shock speed must be equal to the jump in the fluxes divided by the jump in the densities. So that's a consequence of requiring conservation of vehicles, right, which was the fundamental principle, requiring that to hold also when you have a discontinuous solution. So when you have solutions with shock, and therefore you get that the shock speed must always be equal to the jump in the fluxes divided by the jump in the densities. Mathematically, that is called the Rankine-Guilleneau condition. Let me go back a little bit. If you look at the fundamental diagram, what this means is that if you have a left state here and a right state here, and you connect them by a straight line, right, by a secant to that fundamental diagram, the slope of that line will exactly be the difference in fluxes divided by the difference in density. So the slope of the line will be the shock speed. So if I connect this left state to this right state here, the line will be positive. The shock will move downstream. If I connect this density state with this density state, then I will get a shock that moves backwards along the road because I would get a negative line. So very intuitive connection that gives you the shock speed. And if you zoom it out enough, that is what highways must have if you have a shock and just a constant state here and a constant state here. This is what the speed of the shock must be, right? Influx minus outflux divided by the density ratio, because it's conservation of vehicles. Okay, so but mathematically this can all be put into this nice framework of weak solutions. Now there's a few more caveats when you look about weak solutions. For example, one is that you suddenly get too many solutions. For example, you could get that you can also get a weak solution that is a downward jump in density. So you have very dense traffic and then you have very light traffic suddenly here. And you can also make sense of a moving discontinuity. But then you might get other solutions that are also valid weak solutions. For example, two shocks that move at different speed, or a whole what is called a rarefaction fan here. So it becomes a solution that suddenly is continuous and moves sideways. All of these are valid weak solutions. So you have a problem here because you get one single initial condition, but you get infinitely many possible weak solutions. So one must provide an additional condition that singles out one single unique solution that is the real one, the realistic one. And now, of course, again, it's a mathematical problem on the one hand, it's a practical problem on the other side. So in practice, one way to provide such a criterion that singles out one is the idea of vanishing viscosity. The idea is that, well, I know in reality there are no exact discontinuities. There's always a zone. It's just very slim. So let me smear out the solution a little bit. So let me add a little bit of viscosity that smears out the discontinuity, makes it smooth. And now, of course, when it's smooth, then the method of characteristics kicks in again because it's a smooth solution. So if I have something that is a sharp downward jump, I smear it out a little bit, it becomes smooth. Then the method of characteristics tells me the congested points move to the left, the free flow points move to the right, and therefore the right solution is this one here, because now I let the amount of smearing go to 0 and I will get exactly that profile here. So when you have a downward jump, you should not get a moving discontinuity, even though that would be a valid mathematically weak solution, but instead what you actually should get is this profile that is continuous and is called a rarefaction fan. This can be equivalently formulated as entropy conditions or simple intuitive descriptions, for example, that the principal characteristic curves must always go into a shock. If you have a traveling discontinuity where the characteristic curves come out, that would not be a valid solution because you can perturb it a little bit and get a very different solution. So it's essentially robustness to small perturbation. That is one possible way to rationalize this principle. And once this is done, weak solutions with a suitable entropy condition, you have a well-posed problem set up that for a given initial condition gives you a unique solution that also has suitable continuous dependence on the data. All right, so that is,
we're almost at 9 o'clock. So we're almost at 9 o'clock. So just a time when a good breaking point is.
Yeah, so please keep on asking questions. Okay, good, yeah, yep.
Darius.
Okay, one question to, it's a nice way to actually recognize the shock waves, but I was wondering about your fundamental diagram, which is basically this peak. You were saying that the peak is always halfway through the density, but if you look at the roads, usually the peak depends also, like on the country, I would say, on the skill of the driver. Like you see countries where cars are driving a lot higher, with a lot smaller distances to each other, like say Italy.
Yeah.
And you have countries where people keep larger distances to each other. So you get this peak at different positions. And I think what happens often on the highway is that you have a block of experienced drivers driving with a different peak density, which suddenly hit another part of the road where less experienced drivers creating a different peak, yes. And that's also creating a shock wave.
Yeah, there's a lot of really interesting aspects, right? So this last aspect actually, on real roads, of course, you can encounter systematic clusters of drivers that are different from another one. So these models, of course, if this is what systematically happens, these models would fail to describe this because you just have a single density variable, right? So there's some assumption of well-mixedness that happens. These models, by the way, don't explicitly are not explicitly limited to all drivers being identical. It's just that the variability would average out suitably so that you can still capture the key trends in these models on that last aspect. Now, but if you have something well mixed, that the fundamental diagram, I said before, the characteristic shape is uniformly true across the world, but there's quantitative detail. So where is that density, the peak density, right? The critical density. What is the associated flow rate that happens? That is actually different, not just across different countries, but even within the same country. Very simple example, you take a road and then there's a slight incline, doesn't need to be much, right? Like 0.5% of incline. That generally will already change the fundamental diagram that you observe, even though you're in the same country along the same road, because a few cars will just slow down a little bit and it will shift fundamental properties. More obvious example, the slope here that this comes out is the speed limit, or the speed that cars have when they are alone on the road. If you suddenly are at a spot where you have a different speed limit, right, 55 instead of 65 in the US, obviously the fundamental diagram will obviously change right away, right? So yes, this fundamental diagram in practice will be space dependent, and when you have your detector, your sensor units, you can actually measure it at different spots. Absolutely, right? So in reality,
I thought also, that this would even explain the shock waves you see basically kind of approaching different speed zones.
Yes. So first of all, the concept of the shock waves that I explained here is not restricted to this shape here, right? It holds for any flux function as long as it is not having inflection points. That would, I mean, one can still make sense of that, but that would produce weird effects. So let's assume they're concave down always, but as long as they're concave down, and continuous, you can make sense of them in this theory that I described there. What the things will be quantitatively, however, that will of course depend on how these things look like. Exactly right. Yep.
Okay, thank you.
Another question from Stan.
Very quickly, beautiful talk, first of all. Second of all, you made one very lovely fact you didn't mention is that the rarefaction wave has some sense, has some meaning. It's, for example, when the light turns green, that is the solution to the flow. Are you there, Benny?
Yeah, I'm here. I agree. So similar example exactly is modeling red light, green light, right? Or the traffic had to be blocked because of somebody putting poles on it or doing some construction or an accident, right? And then you release it, then what would happen, right? What these models predict is that you will get that fan, right? It's sharp in the beginning, it will flatten and flatten and flatten and flatten up to infinity essentially. By the way, at some point, these models, like this rarefaction fan being clean, at some point, other effects will actually happen in real traffic flow, right? So these models, again, are wrong, right? But in the beginning, at least, that pattern of not everybody at a green light starts at the same time, but actually the first car starts first, and it takes some time to get to the other ones, is beautifully described exactly by these effects. Yep.
Yeah, unlike what happens, for example, if they were all linked together with a train or something, when it just jumps forward.
Exactly right. Yep.
So the entropy condition makes a lot of sense right here, and it's beautiful. That's all.
Mm-hmm. Absolutely. There's lots of beautiful writings also in books. So that some books and mathematical stuff, like they have all these really cool examples, and I would happy if anybody's interested to point at some stuff that I like also. So there's a lot of beauty in this. One thing we have to keep in mind, of course, is that ultimately reality is not exactly this, right? So one still has to be aware that there's other things.
Okay.
Yeah. All right. Well, let me make sure that we are at a good transition point here. Let me actually show definitely this slide here still, okay? Because that is a segue definitely into other aspects as well. So this is an initial condition, and I'll just show you how the video looks like. I hope everybody can see this reasonably smoothly. Does that play for people? Yeah, so you see the temporal evolution of what happens to the density, right? So the density started out with this initial density, and then you see the characteristic flattening at the downward gradient. You see the characteristic sharpening at the uphill, right, of as cars become more dense. You also see that the two shocks can collide, right, on the left. All of this is perfectly described by the theory, right? And keep in mind that, of course, you see the cars there at the bottom. This is macroscopic, but the little cars, the black dots you see at the bottom, they are a microscopic realization. A consequence of the shock is that cars drive with a constant speed and then instantaneously change the speed to something else, which of course we know physically is impossible, right? A car has a mass, right? It's 1.5 tons. So this is a mathematical idealization. The braking zone is collapsed into essentially a jump discontinuity. But the characteristic shape of traffic jams that we see, namely that you have a low density, then a sharp transition zone, and then a high density, and potentially that flattening that Stan mentioned, the green light effect here, that is described quite nicely and quite characteristically. So that is what this logarithm-Richards model is able to describe. But there are shortcomings to the model. One is that obviously you prescribe a functional relationship between the density and the flow rate, and therefore the speed, right? Or the speed and therefore the flow rate. So the model will always, when you look at this solution here, any solution, and you locally evaluate density and flow rate, you will always get something on this red function. But we know that real data has a spread. And this is aggregated over 30 seconds here, right? So despite aggregating over 30 seconds, you have a systematic spread. So there's something in reality there that these models don't capture. Okay, and by the way, this is not just sensor noise, right? Because you see that this is much more localized here, despite noise being present, right, in the sensors. So this is systematic, right? So there's something that they fail to capture. And another thing that actually these scalar hyperbolic conservation laws satisfy is what is called a maximum principle. Maximum principle means that the maximum of the solution at any time cannot exceed the maximum of the initial conditions, and the minimum of the solution at any time cannot be lower than the minimum of the initial conditions. So now imagine you start with a uniform flow profile, all cars equispaced go with the same speed, and add a little bit of a perturbation, okay? But very small perturbation. Then the maximum principle prevents that perturbation from amplifying. It has to remain within the bounds that you prescribed initially. So instabilities, phantom traffic jams, the phenomenon that you start with initially uniform flow and then it slowly develops traffic waves, stop and go traffic waves, instabilities. These phenomena exist in reality, and they're not captured by these first order models. So if one wants to capture these non-equilibrium effects, so this is all equilibrium, right? You're always on this curve here, non-equilibrium effects and these things, then you need to go to second order models. So what I will continue tomorrow is give a brief glimpse here on how to do this in systems that you get here. So these 2x2 models here, they can capture some of these effects and then give you, and let me actually finish the presentation here by just showing this here. So that was the Seminal experiment by Sugiyama and collaborators, where they placed cars on a ring road. Initially, they start with a uniform flow profile, cars equispaced, all going at the same speed. Obviously, there's always perturbation, there's always imperfections, right? The question is the uniform flow dynamically stable? Meaning, do these small perturbations dampen and bring it back to the uniform flow, or is it dynamically unstable? And the small perturbations amplify and drive the dynamics towards some different state that's not a uniform flow state. And what you see here is you systematically get a different state. Uniform flow is unstable, dynamically unstable, and what you get is this traveling wave solution that actually goes backwards along the road, and you see it traveling backwards here. And that has been reproduced by other researchers, including our team, in experimental setups, and this is really systematic that this happens. So that's what people call a phantom traffic jam or stop and go wave that arises out of it. And here is a calibrated macroscopic model. The vehicles down here are just for visualization purposes, but this is a calibrated macroscopic model that captures this aspect. You see small perturbation of a uniform flow amplifies, and what you actually get in time or by the model is that blue curve, right? So you get that traveling wave. You see what it does to the vehicles down here, but that's just for visualization. It is a macroscopic description in terms of traffic density that captures this phenomenon via principled models that produce these phenomena. So I'll talk a little more about this tomorrow, and then of course segue also into a microscopic description.